Hi everyone, I'll be presenting the poster Rapid Prototyping of Coflow Microfluidic Devices for Red Blood Cell Aggregation. This work was done in collaboration with myself, Dr. Marianne Nayak, and Dr. Catherine Mivopoulos. So just an overview on the work that we've done. The purpose was to design, optimize, and prototype a microfluidic device that can be used to investigate red blood cell aggregation under controlled shear rates. So in order to achieve this goal, multiple steps were taken. So the first step was to test different microfluidic geometries and flow rate ratios with computational fluid dynamics. And essentially, we wanted to acquire a linear velocity profile in the blood layer. This would provide a constant shear rate across the entire blood layer. And I'll be discussing this further. The next step would be to actually take the CFD results and actually design a usable microfluidic channel in CAD. So adding inlets and outlets that are compatible with current syringes. Finally, it was to prototype the actual device and test it out. So for a little bit of background, red blood cell aggregation is the formation of stacks or clusters of red blood cells. So if you look at the first figure in the leftmost column, you can just see an example of these clusters. And studies have shown that red blood cell aggregation can indicate abnormal physiological conditions such as inflammation or infection, so making this a worthwhile phenomenon to study. So there's actually many factors that can affect shear rate, affect red blood cell aggregation, and shear rate is the one that we're most interested in. So there's an inverse relationship between shear rate and red blood cell aggregation. The higher the shear rate, the less aggregation, and the lower the shear rate, the more red blood cell aggregation occurs. So essentially, we would like to use Coflow microfluidic devices. If you look at the second figure in the leftmost column, a Coflow microfluidic device is essentially the flowing of two fluids, a less viscous fluid flowing alongside a more viscous fluid. And the less viscous fluid would apply a shear rate in the more viscous fluid. In this case, the less viscous fluid would be PBS, and the fluid of interest is blood. So ideally, we would like a linear velocity profile in the blood layer, as that'll provide a constant shear across the entire blood layer. And in the last figure of the leftmost column, you can just see one of the previous microfluidic devices that we've been testing with. So in terms of the methodology, in the CFD, we used an Eulerian multi-phase model using a volume of fluid method. The flows were assumed to be laminar and steady, and the ratio of flow rate was 8:1 of PBS to blood. So as you can see, the first image on the second column is just an image of the CFD trial. The image below that is actually the velocity profile across the entire channel. So it's a little bit hard to see, but essentially around -2, it's a little bit blurry, but in the middle of the graph toward the top is actually the blood layer achieved in CFD. So we're receiving an almost linear velocity profile. So this is close to what we would like. So after the CFD, it was time to prototype. So CAD design was made of the channel with the addition of Luer lock inlets and outlets in SolidWorks. After the CAD design was made and any modifications were done, it was time to actually prototype the microfluidic device using resin 3D printing. So initially, the entire device, so if you look at the last figure in the second column, initially that entire device was printed using resin 3D printing. However, after maybe a day or two, there would be warping at the bottom and the channel would be very opaque. So then the way to solve this was actually print the top of the channel without the bottom onto a glass microscope slide. So there would be no bottom. The bottom interface of the microfluidic channel will have the glass slide. This improves optical clarity and prevents the warping that we were seeing. So the last figure, so this hybrid design can be seen on the first figure of the third column, and the last figure of the third column is just kind of us testing out for leaks and just showing the overall flow. So overall, it was successful to create this hybrid design, and this hybrid design possessed more optical clarity and durability than the initial prototype. So the next steps are actually to test out and verify the results of the CFD trial using PIV on this microfluidic device. And in the future, we'd like to add an ultrasonic sensor to further characterize red blood cell aggregates. Thank you for listening to my presentation.
Thanks. Dr. Gutierrez, do you have any questions? So the first question is that have you encountered any issues in terms of controlling the flow rate?
So at this point, I haven't actually been able to connect it to syringe pumps yet because most of the equipment in the lab we're trying to fix it so we can actually test it. So I haven't actually gotten a chance to test controlled flow rates in the actual microfluidic device. So I didn't get a chance to look into that.
Yeah. And in terms of your figure, the picture there, have you encountered any microbubbles along the line that will impact your study?
So I kind of, when I was just doing my initial testing, just because as I was taking out the fluids using just plastic little pipettes, there was some, but then after I did another trial, I was careful not to put any bubbles just by kind of squeezing the fluid out in a controlled manner. There wasn't. That's something I would look into, especially towards the higher flow rates, just because the syringe pumps may have some kind of instability. So that's something I would be looking into.
Okay, thank you.
Dr. Gorbet, do you have any questions?
Yes, I do. Thank you. I may have missed that when you were presenting the poster, but I was trying to understand a little bit the purpose of the device, because I know you're trying to look at aggregation, but are you trying to then eventually study it? Are you trying to make it as a diagnostic tool in a way, because you mentioned that it's important, it can help with some of this, to kind of understand what's, where is going to be the next step eventually for this?
Okay, that's a great question. So currently the next step is to actually be able to study aggregation just itself under different shear rates. And if that's possible, then we would like to actually use it to maybe kind of detect. So after we gather a specific set of flow rates that aggregation occurs and doesn't occur, then we would like to try to use it for diagnostics, such as someone with abnormal physiological conditions may have aggregation at a certain shear rate that normal blood does not aggregate at. So for now, it'll be just used for studying aggregation, but in the future, longer down the road, we'd like to use it for a diagnostic tool.
And in relation to that, I just have another question, and I'm obviously not an expert in that area, but I know someone that is, and we've often talked about using chip to look at shear flow with blood, but the problem, the microfluidics have very different flow system and equation in a way than what you would have in other literature that you would have seen. So do you envisage that potentially that you're going to have almost to start from the start, looking at some of what you see in your chip versus what some other people may have seen in, larger tube aggregation has been studied under flow for many years already. And so potentially, clearly identify the flow system into your chamber might be really important.
Yeah, that's definitely something that I would have to look into, but for now, like we're at the early stages, so I'll have to look into that later on.
And Dr. Bai, do you have any questions?
No, yeah, I had a similar question as other judges already asked, so I'll pass.
Okay, good.